Hello, everybody. So in this video, we're going to start the discussion on one very important parameter about the fluids, which is the viscosity. Viscosity is one of the very critical parameters that define the fluid flow, or one very important fluid property in general. And it's like density. Density and viscosity are the two most important properties. So we already discussed density, so now the turn is to discuss viscosity. So viscosity is, from a conceptual point of view, it's equivalent to the friction when it comes to solids. It's going to be equivalent to this in liquids. So it represents how much resistance the fluid is doing to the motion. So, for example, if you consider a case of a solid that is being pulled or pushed, the friction between this surface and the body is what resists the motion of the body. The same thing for fluids. So, if somebody is walking in air, for example, يعني, this is what we do all the time. That you don't feel resistance to flow to your motion while you're walking compared to moving in water. So if you're walking in water, you will feel much more resistance to the flow than what you would feel in case of air, and it will be more if you are walking in oil. So this resistance is due to the difference in the phase or the fluid that you are traveling in. So this is because the viscosity in oil is higher than that in water, higher than that in air. So we can these are two nice videos that discuss this in an experimental way, just to give you an idea what you are looking at here. So this is an experiment with 4 different fluids or liquids: honey, maple syrup, corn syrup, and dish soap. And this is a surface that is like the same distance for each surface, and there is a line here at the bottom. You can see this line, and the same amount of each of these, and equal amounts of the 4 fluids, is being poured at the same height. And we are now monitoring how fast the fluids are flowing. So you can see that they are not all flowing with the same speed, despite they all have, or they are all liquids. So you see that the honey is traveling in lower speed than the maple syrup and dish soap, and the corn syrup and honey are the slowest. So this is because the fluid is, or the 4 fluids have different densities. And the rest of the video is a good thing that we discussed before, that we deal when we discussed the shear force, and we said that we are very interested in the shear force in fluid mechanics because we discuss, or we consider, the fluid as layers sliding over each other. So this is what you'd see here, that if it's a fluid that has high viscosity, then the cohesion force between the particles is strong, and this makes the sliding of them or sliding a layer on the other is hard. So it takes a long time. And in case of low viscous fluids, then the cohesive force is not that strong, so the viscosity is low, and then the fluid can travel with high flow rate, which is a very interesting thing. Now we can see here that this is again, let's start from the beginning. This is a tank that is filled with oil, and there is a ball that is falling. This is a long video. I just cut part of it. The link is already here. And the ball is left to fall freely in the oil. If this is falling in air, it would be in a split of a second. It would be on the floor, but it's taking time because of the resistance of the fluid to flow. So this is what we want to get out of this, that there is a drag force that resists the flow, and that the speed of the flow will depend to a very large extent on the viscosity of the fluids. We are going to go, and after this slide, through the equations that we use to express the viscosity. But before this, we need to discuss this no-slip condition. It's a very important thing that we are going to build our or part of our discussion on. So here This is a needle, a syringe needle, and this syringe or the syringe is filled with a dye, colored liquid, and there is what you see here is a tank that is it's not a tank, or maybe part of a pipe, where a transparent pipe. So there is a fluid that is flowing here. You cannot see the flow of the fluid because it's transparent fluid, so you cannot see it. So there is a fluid flowing in the from right to the left, and this is this part here at the bottom is the surface, the bottom surface of this duct or this container. So the needle is going to go down now, and it's this is an important part here. This needle is now touching the surface. So the dye that's coming out of this needle is going to touch the bottom surface of the container. It's not just flowing; it's going to hit the surface of the container. Um, and this is what you see here. Of course, the liquid is flowing to the left, as you see here, because of the continuous flow that I mentioned before. And what you see here is that the liquid is sticking here, and this is the important part, that the liquid is sticking to the surface, or the dye is sticking to the surface. It doesn't come out until it is physically brushed or cleaned from the surface. So this means that the liquid that was touching the surface was sticking to it, so it didn't leave. It was sticking to it, and this is what we call the no slip condition. So by this no slip condition, we mean that the layer that is touching a surface will have the same velocity of the surface. If it's stagnant, it will be zero velocity. If it's moving with a velocity v, then it's going to be or will have the same velocity. So this is a very important condition that we will keep using until the end of this course. So now we want to see the equation that we are going to use to describe the viscosity. So the simple system that is being used in all the textbooks to discuss the equation that describe the viscosity is two parallel plates, sometimes called the co-wet flow. It's two parallel plates, and the space between the two plates is filled with fluid, and the spacing is L, and the area of the plate is A. The bottom plate is stationary, and it has zero velocity, and the top plate is there is a shear force applied on the top plate, so it's being moved in the horizontal direction with a speed v. Okay. And this is going to be the y dimension. This is y0 and this is y equal to L, and y will increase from 0 to L in this region. Of course, we are interested in the fluid. Okay, so I don't care about the plate at the top and the plate in the bottom. I'm interested in the space between the plates, which is filled with fluid. But we don't know the velocity of the fluid. Okay, and this is why we mentioned the no slip condition at the beginning, because using the no slip condition, we can now tell that the very last layer of the fluid that is contacting the top plate, will have the same velocity of the top plate, and the very last layer or the bottom layer in the fluid that is touching the bottom plate will have the same velocity as the bottom plate. So now we know the velocity of the fluid at the very first layer, and the fluid at the very last layer. Okay. So if the plate is sliding, so it's going to go from this state to this state after sometime. We'll discuss it as, or consider this as, very short time. So this is going to be a very small transition in the distance. So now we know that the velocity here is 0 and the velocity here is v, so we can draw what we call a velocity profile. So it's just a demonstration of how the velocity is changing from the bottom plate to the top plate. So this is how the velocity profile will look like. It will be maximum here and minimum here, and it will keep decreasing from the maximum to the minimum. And now we can describe the shear force as the force divided by area. This is the force and this is the area. So this is tau, which is the shear force, the shear stress. I'm sorry, this is the shear stress. And we know that if this is an assumption that this is a laminar flow, we will discuss the laminar flow later. But let's just take a very simple case now that the velocity profile is linear. Okay, this is the simplest case, that the velocity profile is linear, meaning that the change in the velocity with distance is constant. Delta y over delta or delta u over delta y is constant. So the velocity as a function of y is constant multiplied by the velocity, which is a linear relation. Of course, the intercept is zero. There is no constant here because at y equals zero, velocity equals zero. So u will be equal to zero if the y is zero. So the y over L is the slope. You can just say that u over v is y over L. Okay, this is the slope of this line. Okay, which is du by dy. So we can write it as u, which is function of y equals y over L times v, or we can write it as in a differential form, which we like more, which is du over dy equals v over L. So this is how we can describe the what we call the rate of shear strain or the rate of deformation. Okay, this is what we call the rate of deformation or rate of shear strain. This is a very, very common term in fluid mechanics. Now we can, we need to see how this relates to the viscosity. Of course, we expect that if we apply the same force, then the velocity would be higher if we have low viscosity, fluid with low viscosity, and it will be small velocity if it's high viscous fluid. So now we can we will do like some mathematical manipulation to the equation. So let's say that this fluid, or we did the transition of the top plate over very, very short distance of time. I mean the short time, which is a differential time dt. And in this dt, there is a small deflection here with an angle d beta, and the distance here is dA. Okay. So we know that the velocity is the distance over time. So the dA, this small distance dA, is v times dt. And we know that this angle is very, very small. And from geometry, we can say that d beta almost equals to tan d beta. Okay, tan theta equals theta if theta is very, very small. And this tan equals the dA over L. Opposite over adjacent, and we know that dA equals vdt, so it's vdt over L, which is, if you go to the previous slide, we say that v over L equals du by dy. Okay, so it's du by dy, which is v over L, du by dy multiplies by dt. So now we can rearrange the equation to be d beta by dt is du by dy, and we know experimentally, and this is something we know experimentally, that the rate of deformation, which is d beta by dt and du by dy, and what we know is d beta by dt. This is what we can measure easily. You can measure the angle, and you can do the experiments for different fluids with different angles, and for each angle you can see the relation between the shear force and this angle. So we know that the relation between the shear stress and d beta by dt, it's directly proportional, something we got experimentally, and that this equation can be rewritten in an equality instead of proportionality. And to put it in an equality form, it has to include a constant, and of course, we know that d beta by dt is du by dy, so d beta by dt will be replaced by du by dy. So we know that tau equal is directly proportional to du by dy, and this constant is the viscosity. And this is why we are discussing this now. The viscosity is the constant of proportionality for this equation. This is what you see here, that there are relations between the shear stress and the rate of deformation for different fluids. You have it for air, for water, for oil. And of course, the air is less viscous than water. Water is less viscous than oil. And as the viscosity increases, the slope increases. Okay. if this relation, again, this is the simplest case. If this relation is linear, then we can write the equation in this form, that tau equals mu du by dy. And in this case, the fluid is called the Newtonian fluid. This equation is called Newton's law of viscosity, which is a very, very famous law that we used to discuss or describe viscous fluids, or the viscosity of fluids, or the relation between the shear force and the shear strain. So this is the Newton's law of viscosity. The viscosity is the slope. We call it viscosity or viscosity coefficient, and it takes the symbol mu. Okay. Of course, mu is function of different things. Most probably, or most important of them, are the temperature and the type of fluid. The last thing I will mention here, and this is a very important thing, which are the units of viscosity. And of course, we know that the units are very important thing. And if you're told that there is a fluid that has, or you're discussing the density of a fluid, of course, you'll know that the density is mass over volume. So the same here. We can so from the equation you can find the units. So we can discuss here the units of viscosity. The viscosity has we can predict it from the equation. Tau is a stress, which is force over area, which is Newton over meter square. This is velocity, which is meter per second. Y is the distance in meter. So viscosity will have the units of Newton second over meter square. Newton per meter square is Pascal, so we can put it as Pascal second, or kilogram per meter second. This is one very famous unit of viscosity. There is another unit which is very famous, which is called poise. And poise is the CGS unit of viscosity, which is gram per centimeter second. If you do the unit conversion from kilogram per meter second into gram per centimeter second, it's 10 times. So 1 Pascal second is 10 times the poise. And we know the centi prefix for the units. So 1 Pascal second, or 1 poise is 100 centipoise. So 1 Pascal second is 10 times 100, so it's going to be 1000 centipoise. Centipoise is a very, very famous unit of viscosity. It might be the most commonly used viscosity units because of what you see in this table. The values of viscosity in the SI units are very large. Usually are very, very large. I mean very, very small. So it's 10 power minus 3, sometimes 10 power minus 4, sometimes power minus 5 even. So the Pascal second is a large unit for viscosity. So we like to use centipoise because it's a small unit, so it makes the numbers easy to deal with. So instead of saying it's something times 10 power minus 3 or minus 4, you can find it around 1 plus or minus, or around the ones or hundreds, or tens. So it makes the numbers more convenient to deal with. Okay, so this is the last thing to mention here. So I'll stop here and we'll continue next time, inshallah. See you then.